Interest in next-generation solar cells has recently surged after Elon Musk spoke about the potential of space-based solar power. In South Korea, work to commercialize perovskite solar cells is also progressing. But what exactly is perovskite, and why is it drawing so much attention from researchers worldwide? How solar cells work, and the limits of silicon. A solar cell is a device that converts sunlight into electricity. It absorbs light, causing electrons to move, and this flow of electrons becomes electric power. Today, the most widely used solar cells are made of silicon. Silicon is a semiconductor that controls the flow of electricity well. Given its abundance on Earth and its durability over decades, silicon has become the material at the heart of modern solar cells. Silicon is far from perfect, however. It converts light into electricity most efficiently, only within a specific energy range. Light that is too weak passes straight through unused, while light that is too strong sheds some of its energy as heat. These physical constraints mean there is a ceiling on how much the efficiency of silicon solar cells can be improved. What is perovskite? Originally, perovskite referred to a specific mineral. Today, the term describes a group of materials that share the same crystal structure. In other words, it is not a single substance, but a family of materials with a similar arrangement of atoms. Perovskite materials absorb sunlight extremely efficiently. While silicon requires a relatively thick layer, perovskite can absorb a large amount of light using a much thinner film. By changing the combination of elements, scientists can also control which wavelengths of light the material absorbs best, giving it great design flexibility. It is these advantages that are drawing attention to tandem solar cells, which pair a perovskite layer with a conventional silicon cell. Under this design, the perovskite layer absorbs high-energy light first, while the silicon layer captures the remaining light, enabling a greater share of the sun's energy to be converted into electricity. The manufacturing process is also different. Silicon solar cells require complicated production methods involving very high temperatures to melt and purify the material. Perovskite solar cells, on the other hand, can be made by spreading a liquid solution into a thin coating, which could reduce manufacturing costs. Challenges that remain. Despite its advantages, perovskite still faces several challenges. The biggest issue is durability. Perovskite is sensitive to moisture and high temperatures, so its performance can decline over time. Since solar panels are expected to operate reliably for 20 to 30 years or more, improving their long-term stability is essential. There are also environmental concerns. Some of the most widely studied perovskite materials contain lead, so researchers are developing technologies to reduce their environmental impact when the panels are recycled or disposed of. Although there are still obstacles to overcome, perovskite solar cells have advanced remarkably in a short period of time and are now considered one of the most promising next-generation solar technologies. Rather than replacing silicon completely, they are expected to complement its weaknesses. Researchers around the world are watching closely to see whether this new material will lead the next generation of solar power.